Good afternoon, all of you guys. Good morning. Okay, so we're going to start talking now. We're moving on kind of from triangles to figures that are larger than triangles for the most part. We're going to start talking about parallelograms, but before we do that, in general, I want to talk about polygons and what a polygon is. Does anyone know what the prefix poly means?
Many.
Many means many. So what's an example of another word that starts with poly?
Molly.
That rhymes with poly. Okay, Miguel, polytheism. What does polytheism mean? Your religion believes in many gods. Okay, so poly means many. All right. So a polygon is a many-sided figure. So a polygon is any closed plane figure that is formed by 3 or more segments. So that means that the smallest it can be is 3. It could not be 2 segments. Why not?
Because it won't actually form a figure.
It wouldn't close, right? So if you had 2 segments like this can't be a polygon because it has to be closed. So that's one of the keys, is that it has to be closed, which means it can't have any holes in it. Go ahead.
Okay, when are we going to start doing the thing where it's like the size of the triangle, you do like 2 and then it's like 180? I did it in the summertime. It's like, you count the size and it's like...
Oh, now.
Oh.
Yeah, the interior angles. Yeah, we're going to talk about that today. All right, so a polygon has to be closed. When it says it's a plane figure, what do you think that means? It has to be on a plane, which means it has to be how many dimensions? 2. It cannot be 3 dimensions because that would be on multiple planes. So it has to be closed, 2-dimensional, and it has to be made of segments, which means none of the sides, if they're segments, that means they can't do what? They can't overlap, but they also have to be straight, okay? It couldn't be like a curved side. So for example, here are a group of polygons. These are all closed plane figures. Why are these not polygons? This one right here, why is that one not? It's curved. Good. What about right here? It's 2 separate polygons, basically, right? What about this one right here? That one's open, it's not closed. All right. What about this one? The line goes on, it's not closed either. And then what's wrong with this one here? It's 3-dimensional. Perfect. So this one is not a polygon because it's 3-dimensional. All right. It's made up of polygons. All the faces are polygons, but that itself is not a polygon. All right, so each segment intersects exactly with 2 other segments only at their end points, which is why this cannot be a polygon right here, because it doesn't intersect at the end point. This right here is just a list of common polygon names. You should know them, all right? You should know them and be able to use them. 3-sided is a triangle, 4-sided quadrilateral, 5-sided is a pentagon, 6 is a hexagon, 7 is a heptagon, 8 is an octagon, nonagon, decagon, dodecagon. They stop naming them after that, okay? There's nothing bigger than a dodecagon, but if something has 15 sides, you call it a 15agon, all right? So it'd just be 15gon.
Wait, how do you draw a
15.
A which one? A dodecagon? I mean, it could look like anything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a dodecagon. That's not a regular dodecagon, okay? A regular one would look like, you know how like a hexagon looks? It would look like that, but with 12 sides.
That's 13.
Is it? All right, regardless, you get the idea, right? So you can have an irregular or regular, and we'll talk about that too, okay? Honestly, I would say the biggest ones to remember, people mix up pentagon all the time. All right, means 5, good. And then hex and hepta. Hexagon is 6, heptagon is 7. All right, octagon, think of like octopus, has 8 legs. Okay. All right, so here are some vocab words and parts of it that you need to know. Some of them you already know. All right, a side is each segment that forms the polygon, so all these red ones right here. All right, those are your sides. A vertex is in blue right here. A vertex is the corner where 2 sides meet, so that common end point. And a diagonal is a segment that connects 2 non-consecutive vertices. What does non-consecutive mean? Not connected. They're not right next to each other, okay? So for example, BD is a diagonal. Why is BC not a diagonal? because they're consecutive, so that makes a side. All right, so diagonal is anything that goes across non-consecutive sides. Can anyone come up with what another diagonal would be in this figure? B connects to, oh, E and C, did you say? E and C, good. EC would be a diagonal, all right? AD would be a diagonal. BE would be a diagonal. And what's the other one? AC would also be a diagonal. Good. All right, so those are all diagonals. You'll notice that all of these diagonals, where are they? Inside the pentagon, all right? This or hexagon? Pentagon. This is a pentagon. So inside the pentagon. Good. All right. A, B, and C. Is it a polygon? Is A a polygon? No. Why not? Right here. This is no. Not a polygon. Okay, what about B? No, why not? It's basically two, so they don't have one common end point because it keeps going. All right, what about C? Yes. C is, and it's an octagon? How do you know that? 1, 2, 3, 4, 5, 6, 7, 8. This is an octagon. Is it a regular octagon? No. What does regular mean? Okay, it looks like a stop sign, but more sides. All of the sides are what? Equal, and all of the angles are equal. Okay, so if something is regular, if it's a regular polygon, that means all the sides and all the angles are equal. So that's what it says right here. It's equilateral and equiangular. All the sides and all the angles are equal. So this right here is a regular hexagon. This is a regular octagon. And this is a regular pentagon. All right? Concave and convex polygons. A concave polygon means that in any part of it, a diagonal might be outside of the polygon itself. So for example, looking at this figure right here, which is a quadrilateral, has 4 sides, this diagonal right here, what does it do? It connects those 2 sides. Where does it go though? Outside. It's outside of the figure. So that means it's a concave polygon. All right, whereas down here, and in the one we just looked at, all of the diagonals are where? Inside, so it is a convex polygon. Okay? The way I remember it is when you draw this diagonal, it kind of makes a cave. All right? That's the only way I know how to remember it. So that would be a concave polygon. Is this regular? No, it's not regular. How do you know that? Yeah, the sides aren't all equal. All right, so it's not a regular polygon. Okay, so A. Is A regular or irregular? Irregular. Irregular. Why?
Because all the sides are equal.
Not all the sides are equal. It's an irregular what?
Rectangle.
Rectangle, which more generally is a quadrilateral. Good. Is it concave or convex?
Convex.
Convex. Why is it convex?
They can be diagonal.
Yeah, when you connect all the diagonals, so again, a diagonal means you're connecting the vertices that are not next to each other. So this one would connect with this one, and this one would connect with this one. Where are the diagonals? Inside. Therefore, it is convex. Okay? What about B? Regular or irregular? Regular, because they're all the same. Concave or convex? Convex. Good. They'd all be inside. What about C? C is irregular. Why? What are not all the same?
No, the sides are all
The sides are all the same.
The angles.
Are all the angles the
The
same?
angles are the same.
What angles are not the same?
Oh, the outside one?
Oh, the one for the...
What about, is this an angle right here? Yes. Is that the same as this one? No. So is this regular? No, it's not regular. Is this concave or convex? Concave. Why? If you connected this one to this one, where would you do it? Outside. All right? You made a little cave, so it's concave. It is irregular and it is concave. This one is regular, convex, and this is regular, concave. Okay, there's a ton of vocab there. All right, there's a lot of vocab. Some of it you guys already know. Some of it is new. All right, the concave convex thing is probably new. All right, so at your boards, I want you to do, before you go up there, read the directions carefully. For 1, 5, and 6, you're just telling me if it is a polygon. For 2 and 3, you're classifying it as regular or irregular. And for number 9, you're classifying it as convex or concave. Okay, so you're doing those 8 at your boards. Go ahead. Okay, which one of these is not a polygon in numbers 1, 5, and 6? 5 is not. 6 is not. Justify 5. Why is that not a polygon? Angel? It doesn't connect. Perfect. All right, what about 6? 6 it's a round edge, so that can't be a polygon. Good. 2 is regular or irregular? Appears to be regular. A regular what? Quadrilateral, which makes it a... It is a polygon, yes, that's true. No. Square. Gabe, why?
Because it has equal sides.
All equal sides. Good. Good. If it's all equal sides and it's a quadrilateral, it must be a square. Okay, and then for number 9, 10, and 14, which one of those is concave? 14. Good, because you'd have to use this diagonal to be outside of the figure to connect them. Is number 14 regular or irregular?
Irregular.
Appears to be irregular. Good. All right. So interior angle sums. Tira, I think this is what you were asking about. All right, so interior angle sum. What is an interior angle? We talked about this before break. What's an interior angle? Angle on the inside. What is a sum? When you add them all together. So what we're going to talk about is adding together all the angles that are on the inside of a figure. So if I wanted to know the sum of all the interior angles of this regular hexagon, how could you do it? What do we know so far? It's regular. Okay. So you know they're all the same. Hold that thought. All right. Hold that thought. You've got background information that I want you to hold on to for just a second, okay? All right. So they're all the same because it's regular. There's 6 of them. But do I know anything about how big they are? No? What do they appear to be? Acute or obtuse? They appear to be obtuse. They appear to be larger than 90. But if I've told you one thing in geometry, it's that we don't want to assume, right? So I can't just go up here and be like, that looks like it's about 110 degrees. So I've got to figure out a way to do it. Is there any polygon that you already know the sum of the interior angles?
Yes.
What shape do you already know? Triangle. What do you know about a triangle? It equals 180. You know that a triangle's interior angles add up to 180, right? What could you do with that hexagon? We can split it up into triangles. Can somebody come up and do that? Charlize, you want to try?
Yes. So I guess you would put the dot and then...
All right, there's one. Okay, so go ahead. All right, so that's definitely one way that you can do it. Could anybody make it less triangles than 6? Bianca? All right, hang on for a moment. Charlize, great work. I appreciate it. Bianca's going to erase it, okay? All right. I know, it gets slow. Okay, now it's only 4 triangles. Could anyone make it any less? No? Okay, I agree that 4 is probably the least that you can do, because if you were going to make 5, you'd have to connect 2 sides that are already connected. So knowing this, like if we can make 4, how many degrees are in this triangle? How many degrees are in this one? How many are in this one? And how many are in this one? So what could I do to find out how many degrees are in the whole thing? Add them up. What would be more efficient than adding them? 180 times 4, which is 7. All right, Miguel. 720. Good. 720. So how many degrees are in that regular hexagon? 720. Okay, so how can you find it? You do 180 times 4. All right, that's good. So we drew the diagonals to cut it into triangles. And again, why did we want to cut it into triangles? Because we know the sum of the triangles. Good. How come we had Charlize's great work at the beginning? Why couldn't we use that?
Because it was 5. I mean,
It was 6.
I don't know, yeah.
Yeah, but why couldn't that work? Why do we have to do it this way where you're using diagonals? It's less, okay. Think about, I'm going to erase this right now. Think about if we left it, okay, if we left it like this, what was the first thing Charlize added? A point in the middle. Was that point there before? No? So if you put that in, all of a sudden, you're making an angle in here that's not actually a part of the hexagon, right? So that's why you can't just do those triangles, because all of a sudden you've invented an angle that's not originally part of the hexagon, which is why you have to only connect ones that are diagonals, okay? So that's great, like you can divide it that way, but you're making up an angle that's included in there when it wouldn't be, so it'd give you way too many degrees. All right, so we've got that 720 number. So I want you guys to think about then how you could do that on another shape. What if I gave you an octagon? What if I gave you a nonagon? You could do this for every one of them, right? Do you notice anything about, or can you think of anything about the numbers we did here that might give you a clue how you could use this for other shapes?
That's a 8, right?
This is a hexagon, 6. So the hexagon has 6 sides. What did you multiply that by?
4.
By 4. Okay, keep that in mind. All right, what if I wanted to split up these? Can somebody come try the pentagon? Can somebody come try splitting that pentagon, this figure right here, into triangles? Ivan? All right. Good. Could anybody do it in less? I don't think so. I agree. I don't think that could be any less. So that's how many triangles? 3? Okay. Can somebody come do this one? This is a 1, 2, 3, 4, 5, 6, 7. So that's a heptagon. Can anyone do this heptagon? You want to try it? I think you can. That's perfect. All right, that's perfect. So those are triangles. How many of them are there? 5. Can you say what you said a minute ago? A little louder? You subtract 2. From what? The number of sides. The number of sides minus 2 will give you the number of triangles that you can make. We can use that because in each of these triangles, here I'm going to do 180 times what? Here I'm going to do 180 times 3. So can anyone think of an equation that might work for every single time? The number of sides. We're going to call that, we normally would, but we're going to call it n.
Okay.
We're going to call it n for number of sides. Okay.
N minus 2.
N minus 2. You do know, because what else do you do? Times
Times 180.
180. 180 times n minus 2. All right? And you guys just figured out the equation for the interior angles of a convex polygon. All right? So n minus 2 times 180. Yes? What does that actually get you? The sum of all the angles. All right, so that gets you like the 180 number for triangles. That gets you that number for every shape. So a hexagon is 720. A pentagon ends up being 540, I think.
180 multiplied by 5 is
is the number of all the angles inside it is what they all add up to. Okay, so for example, in a triangle, 180. In a quadrilateral, like a square, all the angles add up to 360. In a pentagon, all the angles add up to 540. In a hexagon, all of them add up to 720. And the reason we care about this, because you guys are asking, like, well, why do I need to know that? Is because then you can find the measure of any of these angles. So if I asked you in this pentagon, or in this hexagon right here, if it adds up to 720, then could you figure out how much this angle is? How? It's a regular one, so how many angles are there? 6. So if it adds up to 720, what could you do to figure out each one? Divide by 6. All right, so each of these angles is 120 degrees. Okay. Last but not least, exterior angles always add up to 360. Exterior angles always add up to 360. So for example, in this triangle right here, 81 is an exterior angle because it's on the outside. These 3 angles will add up to 360. Does anybody have a guess why they add up to 360? For no matter what the shape is. Yes, exactly. So 360 is the number of degrees in a circle. So the exterior angles all the way around adds up to 360. Okay, so in any polygon, the sum of the exterior angle measures one angle at each vertex. If it's a convex polygon, will be 360. It's just always 360. Exterior angles are always 360. What? Well, I just said that. Because it's all the way around it, and it's a circle is how many degrees? 360. So all the way, why is a circle 360? Because that's, if you measured it, what the angles would be. If you drew a straight line like this, Miguel, this is not going to be a straight line because I have trouble drawing straight lines, but imagine this is a straight line. How many degrees is this? 180. How many degrees is this? 180. If I draw a circle, 360. Because it's 180 for the top half and 180 for the bottom half. Because if I got a protractor out and measured a straight line, it'd be 180 degrees. Yeah? Do you want me to get a protractor? Okay, later. I have a tool on the Smart Kit. I'll open it. Okay, so all the exterior angles add up to 360. So how could you solve this to find the value of A?
Add up all the variables.
7A plus 2A plus 3A plus 2A equals what? 360. All right, what's 7 plus 2? Plus 3? Plus 6? Plus 2? 20A equals 360. Every single one of you could have done that. Every one of you. All right, how do I finish? Divide by 20, and A equals 18. Okay, A equals 18. So exterior angles are easy to remember because it's always 360. Interior angles, 180 times the number of sides minus 2. All right, so then go do these 6. Here in numbers 1, 2, 3, and 4, you're finding the measure of one interior angle. So once you use the formula, which is n minus 2 times 180, what do you have to do? Divide it by n, whatever n is, all right? And then down here, find the measure of one exterior angle. Those are always 360. Go to your boards.